Part A asks to find all the values of x between 0.5 and 1 such that sine pi x to the power of minus 1 is 0. To isolate x, we can take arcsine on both sides. So we get pi x to the minus first is arcsine 0. Sine is 0 at 0, pi, 2 pi, etc. We can write out all of these possibilities. We can then continue to isolate x. So the first equation is never 0, so we can exclude that. The others come out to be 1 and 1/2. But this is still not the answer because we can go further by adding pi indefinitely, or more specifically until one of our answers becomes smaller than 0.1. So when we keep adding pi, we see a pattern emerging that looks like the fractions have a series of natural numbers in the denominator. If we continue the pattern, we can write out all of the fractions until 1 over 10. Part B asks to find the definite integral from 1 over n plus 1 to 1 over n of pi x to the minus second times sine pi x to the minus first. And we need to show that this integral takes different integer values when n is even versus when it's odd. We can try a u substitution to simplify this integral. Usually we want to set u equal to the inside of a function in the integrand, such as log, arcsine, or sine. Here we can substitute pi x to the minus first. We could then differentiate both sides and get minus pi x to the minus second dx. This is very similar to the function we have in the integrand. We then need to just not forget to add a minus sign when we substitute. We can substitute by replacing any part of the integrand that resembles the right side of our substitution with du. We can also replace the actual argument of sine with the u. Also, don't forget to change the limits of the integral to boundaries that explicitly involve a function of x and not u, since we didn't actually change the boundaries in terms of u. So now it's a lot easier for us to integrate this simple function. We know that cosine differentiated is minus sine, so it follows that minus sine integrated is cosine. We can then substitute back the substitution for u, so we get the function in terms of x instead of u. Then we can just use the fundamental theorem of calculus and substitute in the limits for the integral and just subtract the lower bound from the upper bound. We can now figure out what the function will be equal to when n is even and odd. To see the value that the integral will take, we can first substitute an actual value, such as 1. This gets us minus 2. We can draw a unit circle to visualize the values of n. When n takes on another, larger odd value, the position of the unit circle remains the same. 3 pi, 5 pi, etc. is the same as pi, and 4 pi and 6 pi are the same as 2 pi. The minus signs for even values of n are switched, so we end up with 2. This means the integral takes on the value of 2 for even values of n and minus 2 for odd values of n. Part C asks to evaluate the definite integral of the absolute value of pi x to the minus second sine pi x to the minus first in absolute value from 0.1 to 1. When we're finding the integral of an absolute value, we must make every part of the function positive. This means we need to break apart this integral into integrals that only consider intervals of the function when it is fully above the x-axis or below the x-axis. What we need to do is find all of the intervals where this function is below the x-axis. Well, this happens when either one of the terms is negative. Pi x to the minus second is never negative, at least not in the given domain. We can find when sine is negative by finding the function's zeros. We have conveniently already done this in Part A. I will quickly draw a hypothetical sketch of the graph using these zeros. It really doesn't matter what behavior the function exhibits. For all we care, it could have looked like this. But the point is rather in the fact that we must flip the graph in parts where it is negative. We don't know and we don't care where it is negative though. We can split the integral into smaller integrals that have boundaries that are the zeros of the graph. Splitting it up in this way guarantees that we will not be calculating at any point an integral that has both positive and negative parts. These integrals go on until the last integral, which has boundaries of 1/2 to 1. I wrote it as 1/1 so it's easier to see that it is a fraction. We can now use the general form of the integral in part B and calculate each of these integrals that we have written out for part C. The boundaries of these integrals follow the same pattern as in the general form of the integral in part B. This form is actually called the harmonic series. But anyway, if we know that this general integral equals to -2 at odd numbers and 2 at even numbers, we can find what the integral of the absolute value of this function would be. The area under the curve of a negative function would be negative. If we take the absolute value of the function, the integral will become positive. So if we just take the absolute value of -2 and 2, we would get the integral of the same function, but the absolute value of it. We can rewrite the original integral as a sum of all these smaller integrals. In total, we have 9 integrals. Since we know that each of them is 2, the answer would be 18. So that's it for this video. Thank you for watching, and I hope I helped you this question. Please like and subscribe. Bye!